Okay, hello, good afternoon, y'all. Today I am back with another video. I am going to be solving for the Laplace transform of sine, using the Laplace transform definition. And so, as we can recall, right, as a matter of fact, you can go to the table of Laplace to find the Laplace transform of sine, right, because it's one of those common functions, right? But in case that you don't remember, and you need it, you're gonna have to derive it, right? So one easy way to do it is by using the Laplace transform definition and using the sine Euler identity, right? So let me go ahead and write that out for you. So sine sine is equal to exponential to the j omega t minus e to the negative j omega. Actually, and it's not t yet. Um, over to j. This is what sine is equal to, right? So let me go ahead and write out the Laplace transform definition for you down here. So this is the way it goes. So we have an integral, right, from 0 to infinity of f of x times e to the negative st dt, right, with respect to time. So what we can go ahead and do is that we can go ahead and take this right here and sub it in for f of x, right? That's what we can go ahead and do. So let me go ahead and do that for you. So we're going to have the integral from 0 to infinity of e to the j omega minus e to the negative j omega over to j times e, or actually let me go ahead and put this in parentheses, e to the negative st dt. Now, this is what we need right here, right? So in this example, I'll be doing the sine, and on the next one, I'll be doing cosine. Um, so I'll be doing two separate videos because this can get a little long, right? So, okay, let me go ahead and go through this. So now, if you look at this, I can actually go ahead and factor out a 1 over 2j and rewrite my integral, right, from 0 to infinity of e to the j omega minus e to the negative j omega, right? Times e to the negative st dt, right? So now we're looking at this, and we can see that we can actually combine our exponentials, right? So what we can do here is that we can go ahead and create two different integrals, right? So I'm going to go ahead and leave my 1 over 2j outside, and I'm going to go ahead and make my two integrals, right? So we make integral number 1, right? In which we're going to combine our first term, our first set of exponentials, right? So we'll go ahead and have e to the negative s minus j omega, and we do the s minus j omega just because we're trying to preserve that positive, right? As you will see. So now we have this right here, right? This is integral number 1, and don't forget your t. This dt minus, because we have the minus because of the fact that this formula right here, right? But our Euler identity has this negative, so we have to, instead of doing a plus, this is going to be a negative, right? So we have a negative on that side, and we're going to have to create integral number 2, which we have 0 to infinity of, let's see, so this will be e to the negative s plus j omega t dt, right? So this is what we have so far, and as you can see, right, these are some. This looks a lot better than this right here, so that's pretty cool. So we broke this function. We broke this function up right here. We we broke this function up into two functions over here, and now we can, this is a lot better to work with now. So now all this is going to take is some algebraic manipulation and just taking the integrals of each of these two, right? So let me go ahead and take the integral of both these. So remember, we still have our 1 over 2j over here. And if I take the integral of the first integral, we'll end up with 1 over s minus j omega. And let's remember it's a minus right there, right? And we'll still have e to the negative s minus j omega t. And remember, this will be evaluated, right? At t equals 0 and at t equals infinity. So the fundamentals, remember the fundamental theorem of calculus, right? Okay, so that's that right there. And so over here, we're going to go ahead and take that integral. But remember, we still have this negative right here. And what does this negative do? It turns it into a positive, right? Because this integral is pretty much going to be, the second integral is going to be the same as the first one, right? But instead, this second integral is going to turn into a positive, right? So we're going to have plus 1 over s plus j omega e to the negative s plus j omega t, and this is going to be evaluated at t equals 0 and at t equals infinity. So that's what we have so far. So now our next step is to do the fundamental theorem of calculus, right? Yeah, so pretty much we're just going to go ahead and evaluate our limits, right? So let's go ahead and do that. So let me go ahead and write it out for you. So I'm going to go ahead and take this and switch colors. And so now what's going to happen is that I'm going to go ahead and write this out as 1 s minus j omega e to the negative infinity minus plus, right? This is going to turn into a plus, right? Because of the fundamental theorem of calculus, which require us to take the subtraction. So now with the two negatives right here, the negative and the negative from the fundamental theorem of calculus, that turns into a plus. So now we'll have 1 over s minus j omega e to the 0 power, right? So that's that one integral. Remember, right? Right now I'm just evaluating this. That's why I'm bringing down the 1 over 2j. I'm just taking and evaluating my two integrals. So this right here, e to the infinity. Oh, I'm sorry about that. E to infinity. This is going to go to 0, right? And e to the 0 is just 1. So therefore, our first integral is equal to, switch colors, 1 over s minus j omega. And this is going to be our first part, right? So that's that part right there. And so now let's go ahead and look at our second integral. So now we have 1. Let me go ahead and separate this. 1 over s plus j omega e to the negative infinity. And because this integral, or because this right here is a positive, because of the fundamental theorem of calculus, we have a negative on our, when we evaluate at t equals 0, right? So now this is going to be minus 1 over s plus j omega, and this is e to the 0 power. Remember, like, e to the infinity is always going to go to 0, right? So that's 0, and this right here is just going to be 1. Therefore, our result in this second integral is just minus 1 over s plus j omega. So this is what we have so far, right? So now this is a major accomplishment, right? Because now we're at this step. We already went through the integral. Now it's just an algebraic problem. Now this is all it turns to, right? This is just algebra at this point. So now we just have to do a bit of manipulation, which I'm not really gonna go over. I'm just gonna go ahead and do it. So let me go ahead and go through it. So we have 1 over 2j, and pretty much it's I'm just going to combine both fractions, right? So you have s plus j omega minus s minus j omega over s plus j omega. We'll write these as terms s minus j omega, right? This is what we have. We focus right there, right, on the inside terms. We can actually go ahead and cancel out some terms. So we can actually go ahead and get rid of the s. And so we can also go ahead and write, we can combine these, and we'll go ahead and write them as, let me see. So as you can see, we'll have 1 over 2j, negative and negative, that's a positive, so we'll have 2j omega. Yeah, there we go. So we have 2j omega over s squared minus j squared omega squared. So this is pretty much what we have, and we can go ahead and cancel our 2j over here. So that leaves us with, we'll have omega over s squared minus j squared omega squared. Remember, j squared is imaginary, right? That's like -1 squared, or I squared, right? So now this is going to go ahead and turn positive, right? Because we'll have that right there. We'll have that negative j squared, and so now we'll have omega, right, over s squared plus omega squared. And this, ladies and gentlemen, is the Laplace transform of sine using the Laplace transform definition. Thank you for watching.